Now let's deal with longitudinal or axial magnification. We know it, in case of longitudinal or axial magnification, the size of image and object is measured along the principal axis. So the longitudinal magnification as defined is length of image upon length of object. Now the definition of longitudinal magnification here also will remain same as we have defined in case of spherical mirrors, and we are denoting it by subscript L. So ML will be VA minus VB UA divided by UA minus UB. Now here A and B are the ends of object lying along principal axis. V is indicating the image distance for the corresponding end, and U is indicating the object distance. Again, for a very small object ML, we can write it approximately as dV by dU. Now we can develop a simple relationship between longitudinal and transverse magnification. Now differentiating the basic equation which we have done for refraction from spherical refracting surface, that is mu2 by V minus mu1 upon V is equal to mu2 minus mu1 upon R. We get mu2 dV over V square minus plus mu1 du over U square, and that gives me on rearrangement, that is mu2 dV by V square will be equal to mu1 du over U square, and this on rearrangement gives me dV over du is equal to mu2 over mu1 into V square over U square. So we get a very simple relationship between longitudinal and transverse magnification as ML is equal to mu2 upon mu1 into M square. Now mind it, this relation is valid for small objects only. Now to understand the application of object image distance equation for spherical refracting surface, let's consider a few examples. The problem on screen says we have an object which is placed 50 cm from the surface of a glass sphere of radius 12 cm along a diameter. Find the position of final image formed by refraction at both surfaces, and we have to take the refractive index of glass as 1.6. Now let's go event by event. The first event will be of refraction, and it will be at air glass interface. So let's locate the pole of the refracting surface, optical axis, that is principal axis, and using appropriate sign convention. Now here mu2 will be 1.6, mu1 will be 1, and U will be minus 50 and R will be plus 12. Making these substitutions, we get V is equal to 160 by 3 centimeter. Now these refracted rays will enter into glass and again will refract out into air. Now this image formed by first refracting surface will act as object for the next interface. Again the sign conventions remains the same. The only difference is now we'll measure all distances from the pole of the second surface. Now making substitutions, here in this case mu2 will be 1, mu1 will be 1.6. Now we have to be very careful while writing the object distance for this second interface. So we get finally 1 over V minus 1.6, and earlier we got 160 by 3, it was positive, and positive meant that image is formed in the positive side, that is in the direction of incident ray. So here we'll be writing it as plus bracket 160 by 3 minus 24. 12 centimeter is the radius of the sphere, so we'll subtract the diameter, which will be 24, is equal to 1 minus 1.6 divided by minus 12. This on simplification gives us plus 9.5 centimeters. That means final image is formed 9.5 centimeter towards positive direction from the pole of the second refracting surface. A proper ray diagram is shown on the screen. Now let's take another problem which is a bit lengthy to understand the refraction from plane surface as well as spherical surface. The problem is shown on the screen. The problem says there is a block cubical of glass and its refractive index is 1.5 and it has a concentric spherical cavity of radius r is equal to 3 centimeter. Now each edge of the cube is 12 centimeter. We have a luminous point object which is located at a distance of 12 centimeter on the left face of the cube as shown in the figure. We have to calculate the apparent position of object when seen from the right side of the cube. Now let's analyze